So, good morning, everyone. Welcome to AI for Highway Maintenance. I'm Jordan Thayer. I'll be talking about how we built a system to help allocate municipal funds for highway maintenance for the next 45 minutes or so. Before we get too deep into the talk, though, let me just give the whole thing away. First of all, AI crops up in really weird spaces. I'm sure that a lot of you, when you looked at the title, like, AI for what now? So I always love that it comes up in weird places, doing strange things. You have to build these systems the same good way that we build the rest of our software. They have to be testable. They have to be explainable. You have to care about the users that are interacting with the system, because if no one uses your software, it's not going to have any kind of impact, really. And finally, once again on the users, what the best answer is and what the user is willing to accept and implement may be different things, and you need to be cognizant of that and play to what the things that the users will actually do. So a little bit about who I am. Hi, I'm Jordan. I did my bachelor's in computer science around here in Indiana in '06. I did a PhD in AI before it was in vogue. And then I spent a bunch of years doing research in AI for the government and for various firms. So a few in static analysis and a few at my current gig as we're a software product consultancy, and I'm the AI practice lead there, or excuse me, the AI strategist. My title changed recently. But the thing is that my senior thesis in undergrad used graph algorithms, and my PhD is in them as well. And that's mostly what I did when I was in defense. And this isn't so much to brag as it is to highlight that I'm a huge tool. And very specifically, I'm a hammer. And I found this nail in the wild. I'm really excited about it, and I hope I can get some of that over to you. But also, I don't know what's a weird term of art and very advanced anymore. I'm just completely lost in it. So if I say something that doesn't make sense, please interrupt me. All right. So how did you all get here today? I drove. Everyone drive, or many of you drive out to the mall, right? How are the roads? Right? We're in the middle of construction season now that winter is over. They're full of potholes, cracks, and whatnot. So this project was about helping states address that issue using AI. We're going to talk a little bit about the problem domain, and then we'll get into the meat and potatoes of how the system was built. I forgot to start my timer when I got kicked off. So we'll talk about why the system wasn't just trivial to produce, and then we'll talk about how the users interacted with the system and how we had to meet them where they were to get uptake. But starting with the problem itself. So here's a picture of various roads in various states of disrepair, and they're all obviously damaged, right? They have cracks running across them. The big thing that happens to highways, like from 100,000 feet, there's a water impermeable membrane when they're laid down. That's part of why they're made with fossil fuels, is to have them be hydrophobic. And eventually that membrane breaks, and then water gets in, and then water freezes, and the road heaves, and that's bad. But there are a bunch of different ways that roads can fail, and they have different underlying causes. So in the upper left, I think from your perspective as well, you see both longitudinal and latitudinal cracks in the road. Those come from different causes, and they both damage the road by breaking the water barrier. But that damage is different underneath it than the damage that causes what's called this scaling, this alligator scaling. That's different. And what causes the dimpling in the center and the potholes, also different. So roads are this big layer cake of various types of stone and asphalt, and any one of them could be the culprit, and how that manifests up at the surface is different. But ultimately what happens is the road's not smooth to drive on, everyone's upset, and then someone calls City Hall and says, hey, this road's bad, please fix it. The scoring system that they use to measure the quality of highways is called PASER. I used to know what it expanded into. I've lost it in this moment. We'll have to Google it together later. But this is a chart put out by the Indiana Department of Transportation. Indiana's where the work was done. PASER is a numeric scale from 10 to 1, 10 being a newly laid road, fresh asphalt, 1 being you probably can't drive a car across it safely anymore. And the state of Indiana and other states in the Midwest expect a road that's unmaintained to decay into rubble over the course of roughly 40 years. This graph shows that trajectory, with PASER being on the y-axis and the time since the road's construction on the X. The scale itself is really interesting. So first of all, it's the unit that all of the highway engineers speak in, so we have to learn to understand it. But two, it's a rating system that was designed with two things in mind. It needs to be fast to teach, and it needs to be fast to score. So people need to be able to look at a segment of highway, make a snap judgment, this is a 6, this is an 8, this is a 4. And they need to be relatively consistent across each other. But note that I didn't say that the goal of this measurement system is to be finely discriminating between different types of failure or incredibly accurate. It's meant to be easy to teach and easy to execute, first and foremost. So we'll come back to that in a bit. Some other terminology that I may use throughout the talk. A segment is a section of highway, a city block, a couple of city blocks. Maybe it's a half a mile of country road. It really is not going to be uniform throughout. It's going to depend on whether or not you're talking to a city, a township, or a county about their highways, because they have different amounts of road, lengths of road that they have to care about. The road network, though, is consistent among all of them. Those are the segments that they have to care about, that they're beholden to the state to maintain. An agency is a group. It could be the company that's running a private industrial park. It could be your town. It could be your county. In some cases, it could be the Department of Natural Resources. And PASER is that scoring mechanism that we were just talking about. So this is the city where I was born, and it's Hope, a small town in Indiana. And even a small town like Hope has on the order of about 500 highway segments that they care about tracking and maintaining. That's a large number of anything to pay attention to as a human being. So what do they do today to do that kind of planning? Well, the first thing that happens is a couple of engineers get in a car. There's got to be someone to drive, and there's got to be someone to do the evaluation. So they've got a map, and they've got a notebook. And the person driving the car looks at the street and calls out a number. And the person with the map and the notebook marks it down and then tells them when to take lefts and rights. And they have to drive at about 20 to 30 miles an hour to score these streets. So you're not going at like highway speed, but you're still rolling along as you do it. After the two city engineers have written everything down, one of them, or someone that the agency hires, is on the hook for building a plan. We have $25 million this year, let's say, as a hypothetical. We would like to spend that $25 million on this collection of roads, and we're going to repave these, and we're going to fix potholes over here, and we're going to do those black snakes that you see everywhere to fix cracks. We're going to do that on these segments of roads. That plan then gets socialized with a responsible entity, usually something like a mayor or governor, township council in some cases. They'll go back and forth with the city engineer, because the city engineer has a set of things that they'd like to see fulfilled, right? They care about the road network in a way that's maybe different than someone with a political eye on it. The civil engineer may be mostly concerned with the average state of highways, and the mayor may be concerned with whether or not they pave Main Street and where the business district is this year to make people want to drive to that part of downtown and buy and sell things. So they go back and forth for a while, and eventually they come up with a plan that everyone agrees on, whether or not they're happy with it, you know. And that has to be socialized to another group of people, usually some sort of advisory or monitoring board. So this is your town councils. This is your public notice periods. Once the plan has been socialized with that group, it ultimately gets bid out. So almost no agency has their own highway maintenance equipment. They do that through third parties. They hire them to come in and do the construction for them. There are a couple of cases where this isn't true, specifically those black streamers that go on the highway and potholes. Often municipalities will have what are called kettles to go fix those, but the big work, that's always bid to a third party. And then winter happens, there's the freeze, and then the thaw, and the cycle continues anew. They are theoretically supposed to go out there and do this process every year. In practice, The high cost of driving the streets with 2 engineers for the course of like a day or two is so high that they actually only evaluate the quality of their streets once every other year. And then if someone calls in and is real angry about a street that they don't think should be one that's causing a bunch of complaints, they might go out and spot check to see why it is that that road decayed faster than anticipated. But that's the general process. So to go a little, there's software that you could imagine building for all of this, right? Anytime I hear someone say, well, I run down the road with a pen and paper and write numbers as someone talks, like, okay, that's dictation. We can make software that helps here, right? Similarly, this is communication and report generation. That's our bread and butter, isn't it? I know that we all may not love touching PDFs, but certainly users do love putting documents to talk about. And building the bid documents that go to the various contractors to fulfill the road and managing that bid process, you can imagine building software here too. So there's an opportunity to use AI in all of these places. The generative stuff that's sort of sweeping the world right now, that would mostly be in these fuchsia and blue boxes. But the AI that we're going to talk about for the rest of the talk is over here in the yellow one, the construction of the plans for allocating the municipal funds and the prediction of how highways degrade over time. So there's one big problem with the current state of how highways are maintained, and that is they get worse over time no matter what you do. So I think we've all probably experienced this. Roads are just bad. The biggest two culprits for that are the municipalities do not have a huge amount of money to maintain their highways. They need something like 10x the money they usually have for highway maintenance to actually stay ahead of it. And what happens is the common wisdom in that world is that you should fix your worst roads. The worst roads are the ones that cause the most complaints. They do the most damage to the vehicles that travel over them. That is going to be your biggest bang for your buck in terms of investment. But what happens is if you always fix your busted roads, you don't have any money to do preventative maintenance on your nice roads. So you repave a small amount of these, and then these degrade and get busted, and now they're in the pile of things that need completely rehabilitated. And at some point, the state level government or the national government comes in and provides you a large bolus of money so that you can fix a huge number of your roads all at once. And then the cycle begins anew where you keep chasing your tail, not being able to really do the preventative maintenance that would help you. How they do it today is spreadsheets. If you've been in software a while, you realize that most of what we do professionally is take things that are spreadsheets and turn them into more robust, bespoke programs. So what they do is they have a spreadsheet that shows every segment of road that they care about for their agency. And they go down that list and they say, I'm going to do this treatment on this highway, and given the amount of surface area of the highway, that's going to cost this many dollars, I estimate, this year. And they do that one at a time. If they're real advanced, they may print out some maps and use some highlighters to say, well, I'm going to repave that segment entirely, and this one is going to get some crack sealing, and this one over here gets no treatment whatsoever. And they'll do that for the whole city, a highway segment at a time. So how do you do that with AI? Well, the trick is we're going to emulate what the humans do. So we're going to write a program that monitors the state of the agency. And there are two things that we care about in the state of the agency. The first is how much money do they have to fix their roads? And the second is what treatments have we decided to do to what segments of roads? So we're going to have our pot of money and all of the roads that we care about written down. And then we're going to say, okay, well, for that first highway segment, what are we going to do? We could do nothing. And if we don't do anything, we don't spend any money doing nothing. So in the future state, we've done nothing to road 1, and we've spent no money. But we could repave it entirely too. And for the sake of argument, let's say that that costs $5 million to do. For space, we'll contract these. And there are actually a bunch of different types of treatments that you can do to highways in the low tens. So I don't want to show all of the potential other alternatives here, but imagine that that goes out for a ways. Well, once we've made a decision about what to do to First Street, our next job is to decide what to do to 2nd Street. On 2nd Street, we have the same set of options available to us, right? We can pave it, we can not pave it, we can crack seal it, and so on and so forth. And what we're going to do is we're going to chain these sequences of decisions together to produce prospective plans for what we might do with the money. And a plan is complete when the money is gone. So we allocate all of the municipality's budget out to the point where we actually can't pave a whole segment of road, but pretend that's $0. It's sometimes in the low thousands. So we'll plan all of these applications until we run out of money. And when we run out of money, that's a goal state in the world of planning. And that sequence of actions produces a hypothetical world with a value to it. And what we're going to do is we're going to walk this huge set of potential outcomes and evaluate each plan of action against another plan of action and take the good ones. Does this look familiar to anybody? Yeah? What's it called? Anyone know? Depth first search. So someone said depth first search. It's a tree enumeration. And yeah, depth first search is maybe the most classic tree enumeration. And for the person who said graph search or graph, it is a graph. A tree is just a very specific kind of graph, one that doesn't have cycles. So I think at some point in your career, either in academia or after you've been in the field, you've had to write like an in-order traversal of a tree. You've had to go through elements in a collection in some way. So the fact that the planning algorithm, the AI in this is something that's about as simple as most of us have seen it in coursework at some point in our career or just having to enumerate a set. What is it that made this particular problem hard and interesting enough to talk about? So there are some things that make this really, really challenging. Understanding the domain itself and then the model of degradation is actually very hard. And of course, there are performance problems when you choose to do an algorithm like depth first search or tree search. So the first and largest problem that we encountered on this project is that I'm not a civil engineer and I don't know anything about highways or very much about government for that matter. So that's the first thing that you have to overcome is we're going to be working with subject matter experts to try and model the domain of interest. And we're going to have to go back and forth with them constantly because I just don't have the knowledge in my head that they have in theirs. So I have to surface the plans that we're making, why we're making the decisions we're making, and then talk to them on the regular about why those decisions are bad or good. Another big issue was that the input data wasn't pristine. And tree search at the scale is inherently difficult. To deal with the interaction with the SMEs looked like this. So we build a model. We built a whole planner out. We were emitting the first automated plans for allocation within about a week or two of starting the project. And we would put those plans in front of the civil engineers, and they would inevitably say something like, "Why are you wasting my time with this garbage? This plan is awful." It was like, yes, the plan is awful, but is it legal? And if it's not legal, let's talk about what we've done that was wrong that we can't do. And once we've eliminated all of the things that are impossible, let's talk about all of the bad decisions we made so that we can understand why those were bad decisions and carve them away from the potential plans produced. And then they'd talk to us for a few hours about the plan, and we'd go away and we'd implement that change set, and then we'd come back a few days later with a new demo. And I hope that this sounds very, very familiar to you, because it's very, very similar to a build, measure, learn loop, right? We're producing part of the product, we're putting that in front of our customers or our stakeholders at the very least to get feedback on the direction we're going so that we can course correct as we go forward. It would have done no one any good if we had built the most whiz-bang performant planner in the world, but didn't actually know anything about highway maintenance and it had just produced very bad plans very quickly. That would have been unsatisfying. Even then, our plans underperformed expectations. So this was after working with the SMEs for about a month. We were now producing plans that were overall much higher quality than that which they were making by hand. So the blue line here is the worst first approach. The standard knowledge within that domain, I'm going to treat my most damaged highways first. Year over year, that's what your expected average Pacer score for your whole network does from a given starting point. It goes down, it doesn't recover, you just don't have enough money to dig out of the hole. We had hoped, and had reason to believe, because of the experts in the room, that by implementing a more intelligent strategy backed by AI, we should be able to overcome that constant degradation and actually raise the quality of highways overall. But we really weren't seeing that return, even with the optimal plans per our model for the area. And when you start to see, okay, well, we've done all of the correct actions, but now the outcomes don't match with the SME's expectation of that plan being executed, then you have to ask yourself, well, what's wrong in the model? And what was wrong in the model was the model of degradation that was published by the state. So the green line is INDOT's published degradation model. They say to their highway engineers, this is roughly what happens for roads. Like there's a bunch of different things that can happen, right? If the ground washes out from under it or there's a flood, you move further on the curve faster in a year than you might otherwise. But in general, in aggregate, this is what we expect to see. But when we looked at the data, we got these yellow and blue lines, or orange and blue lines. The orange one is for concrete roads, and the blue one is for asphalt roads. And we found that they decayed at a much more aggressive pace than the state of Indiana thought. And so if we're planning with the green line modeling reality, but reality actually follows the blue or the orange lines, then our plans are going to diverge from reality very, very quickly, and we're not going to see the expected returns because our models are off. So these two lines, the orange and the blue ones, these are also produced with AI. They're done using machine learning and regression, but there's yet another problem here. Before we get to the problem, though, I often find when we're building software products that you don't just put AI in your product. You're actually grabbing for about half a dozen tools in most cases. And here's where I need to use an optimization algorithm because the user cares about the most relevant search term or the most likely to buy product. But here's where I'm doing machine learning to know what their preferences are so that I can estimate the value of their likelihood of purchase. It's very, very similar here. We used regression to get those models, but the problem was there just wasn't enough data for machine learning. We talked earlier, if you look at the x-axes in these graphs, they both go out to about 40 years, right? Well, the state of Indiana has only been gathering highway degradation information in a way that's accessible. It's not even a database. It's a pile of spreadsheets that you're welcome to look through if you care to. But they've only been doing those since 2018, which is way less than 40 years. And additionally, no one actually lets a road decay to rubble in front of them. The constituents would never tolerate it. So we have to find some way of getting enough data to build a machine learning model to predict how the roads will degrade over time, right? We want to do regression. That's the natural fit here. But we don't have enough data to do regression. So we reach for another technique. Go one more down. We reach for Markov decision processes. Anyone familiar with that term? So the idea is that we're going to build a graphical model, and the only thing that matters to that graphical model is where you are right now. It doesn't matter where you came from. The previous decision could matter, but that's the Markovian assumption. But the entire trajectory of how you got here doesn't matter. That you're here encodes that fact. So in our particular model, we have 10 values that matter. These are the Payzer scores, 10 to 1. And they're always discrete. You can't get a 9.5. It's humans grading it on a 1 to 10. So we look at the data from every agency in the state of Indiana, and we write down the number of times that a 10 became a 9, and a 9 became an 8, and so on and so forth. And we say, okay, great. Now let's write down all the times that a 10 became an 8, and a 9 became a 7, that we took a 2-step, right? And then we'll do it for 3 steps, and then we'll do it for 4 steps, and then we'll do it for 5 steps, and so on and so forth. Once you've got all of those arcs put in with their relative counts, what you have are edge weights, right? You know how many times you went from a 10 to 9 relative to how many times you went from a 10 to 1. You can build a probability distribution. And once you have a probability distribution, what you can do is you can sample random trajectories through the graph, starting at 10, going all the way down to 1 as a terminal state, and look at the sequence of numbers you produce. That is a hypothetical sampled trajectory of a road decaying in the absence of other information, modeled on the aggregate highway, in this case in the state of Indiana, segregated on surface type. You can do all kinds of segregations that are interesting. It turns out that the northern part of the state that gets lake effect snow has very different highway performance than the southern part of the state that doesn't get a lot of snow. But things near, things too close to the Ohio River Valley flood more often, so their highway degradation curves are different too. But the trick is to build an explicit model here that we can use to walk through time, sample hypothetical trajectories. Those can be put back into a standard ML regression model, and you get a formula back that says, okay, in a year, if I'm at this, I expect to be at this point on average. And now all of a sudden, we don't have whole number Payser scores because we've done this regression and violated the integer assumption. But for planning, having the non-integer numbers, the machine doesn't care. It doesn't, excuse me. Payser scores aren't integral because it's well and good and correct for Payser scores to be integral, and roads take a whole step every year. Payser scores are integral because humans are frail and made of meat, and the machine is not and doesn't have to care about keeping 100,000 different degrees of separation. People can't. So the tree search itself that we implemented is also very, very challenging. And I like talking about it because it gives me an excuse to talk about the Hitchhiker's Guide to the Galaxy. So in this particular quote, Douglas Adams is talking about the scale of the universe, how big it is. Space is big. It's really big. You won't believe, you just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down to the chemist, but that's peanuts to space. So if you haven't read Hitchhikers, I strongly recommend it. But it turns out that actual space is just peanuts compared to the search domain that we're considering. In this particular case, the total number of plans that we could consider for a given municipality. And for those of you who know that it's tree search, well, so there are 30 treatments, give or take, that the state of Indiana considers for applying to its various highways throughout the state. And the average agency, or excuse me, the median agency in Indiana maintains 500-ish segments of highway. The biggest ones are in the thousands, and the smallest ones are in the low 100s, but there's no one that has less than 100 segments. And the state mandates that you submit 5 years of planning. So this year, the agencies will have to submit plans that say how they will spend their funding through 2030. And for those of you who shouted out depth first search earlier, you can see where we're going here, right? This is going to be a big number because trees grow and the depth of the tree, right? It's the branching factor to the depth. So what we get is 30 to the 500 times 5, 2,500, right? And that's some factor times 10 to the 3,000 and change. Well, it's estimated that the number of atoms in the observable universe is 10 to the 82. So the exponent on the size of the plan count is 2 orders of magnitude larger than the exponent on atoms in the universe. How do we find anything, like how do we find any of the needles in that haystack, right? That's the whole trick. Well, you work smarter, not harder first. So remember how we said trees grow B to the D, right? Which means that at any point in our tree enumeration, each one of these, so let's say that the top node, that's the root, right? That's a current state of the plan. And each one of these is a different decision that we could make. If we make the right choice, if we're lucky, right, then we save 3 times b to the d minus 1 work. That's, roughly a quarter or roughly a 30th of the work given our branching factor in our problem. So we save a huge amount of labor if only we can guess the right child, right? What's the right action right now? So that's where a technique called heuristics come in. Heuristics are either numerical values or rules of thumb that tell the program, this is probably the right action to take now. Heuristics aren't enough, though. So this is a cartoonish visualization of how depth first search works. In a tree of sufficient size, what depth first search will do is it'll make all of its decisions up at the top of the tree, and then however long you run, it won't actually back up the tree that far because there are huge state spaces to study in the last 5 decisions, right? 30 to the 5 is still a huge number. 30 to the 10 is still enormous. So it'll get stuck in the small corner of the space, and you won't see the full the full breadth of possible solutions in that space, no matter how good your heuristics are, unless they're actually perfect, that's a bad strategy. So there are other types of tree enumerations. One called limited discrepancy search is what we used, that spread the effort out in different ways. And the search strategies that exist here all seek to improve the order in which the possible plans are visited so that you get better plans faster, because all else being equal, that's what you want. So you have to be considerate about how you actually walk through the space. But also you gotta go fast. And there are a couple of ways to get there. By the time we were done wrenching on the software, we were considering 1 million potential alterations to the plan a second. And I don't know about you, but like this is the thing about my job that I love the most. Usually you don't get to do weird Baroque optimizations because they're absolutely the wrong thing to do, right? They're hard to maintain, they're impossible to scrutinize, and then some poor junior, or worse yet, you, is gonna come back to them in a year and be like, what asshole wrote this? But sometimes it actually makes sense, and when it does, it's fun. How do you get there? Well, this is your new best friend. You're going to be in the hole with it for a long time. You're going to use the profiler to figure out where the hotspots are in your code, and then you're going to play whack-a-mole. If you're lucky and you're in a modern language, you've got something integrated with your development environment. If you're unlucky, you're going to spend a lot of time slaving over a hot GDB and gprof. But they're fit-to-purpose tools. Once you've identified the places, here are the things you can do. So this computation, this regression, doesn't seem too bad, right? It's a low-degree polynomial that tells us in a year what will our road decay be like. Well, in a program like this, computing a low-degree polynomial, we're not going to do that. We're not going to exponentiate ever. Division's right out. So what we're going to do instead is memoize it. We're going to write down every possible transition from one Payzer score to another and put it in an array. So that we can just look up what the next value next year is without ever having to do the computation. Because the trick is, I can write that big table down one time and then load it up every time the program runs and never have to do any of those computations in the middle of search. And it lets it go screamingly fast. But you're trading off like, well, I'm going to use like a gigabyte of memory to just write down floating point values. So it can get, trading memory for time is the key trick. You can only push that so far because at a certain point you do need some heap space for your program. Also, conditionals are now a thing of the past. We are not going to let the thing branch because as good as branch prediction is these days, it's still slower than not branching in the code. So there are all sorts of tricks like computing multiple values simultaneously and zeroing out the wrong ones and summing them together that are faster than executing a branch, letting speculative execution run 2 sets of instructions and then cherry pick the right one. So when you see the no branching code techniques, this is where it starts to make sense to use those. Who knows what this is a picture of? Anyone want to shout it out? Yeah, it's a CPU diagram. It's a very like high-level CPU diagram. And a thing that you might notice about the CPU diagram is that there are about 6 of these things called ALUs, and then the floating point register is just the one thing, or the floating point box is just the one thing. So if you're not going to a graphics card, which is a whole different argument, right? That's got a bunch of floating point units, and you can do lots of things in parallel, a very different type of high-performance computing. But if you're staying in CPU land, then you can leverage the fact that most modern chips have about twice the number of arithmetic logic units for integers than they do for floating points, if you can stay in integers. So we had floating point numbers. We could end up with a Payzer score of 7.5, but if you multiply things out and truncate, you end up with fixed point numbers as opposed to floating point decimals. And if you're doing fixed point, you can just stay in the ALU. And so by the time you're done working on this program, you may not know the difference between your shifted units and the original floating point, but it doesn't particularly matter. You just have to make sure to divide out at the end when you do the reporting. So how much did that tuning buy us over the course of the project? This was one of the first performance charts we produced once we were producing plans that were acceptable. So the score on the left axis is a numeric score that we were producing for the sake of the engineers. We'll get to it in a second. Originally on in the project, the civil engineers cared about several aspects of the highway system, and we produced a weighted sum of those aspects that they cared about to evaluate the various plans against each other. But the y-axis is score and the x-axis is compute time in seconds. So you'll see that we find a bunch of good solutions early on with this tree enumeration, and over time we asymptote to the best solution we'll ever find, and we find it around the 5-minute mark and change. You know, that's a respectable amount of time in computation. That's walk away and get a coffee. We ran these things out for days and didn't find further improvement. These spaces are too large to have provably optimal solutions. But the algorithms that we're using here, the tree enumerations, are memory efficient in a way that you can run the computation arbitrarily long if you care to. After the wrenching, though, we were finding our best solutions at about the 15-second mark, which is a very different experience in terms of user interaction. 15 seconds is slow enough that it's obnoxious, right? It's not instantaneous. You see the pinwheel, you think the program crashed. That's still a problem, but it's not 5 minutes and it's not several hours. So we're in this weird no man's land between, well, I'll just send an email when the task is done, and it's quick enough for a person to sit through. Theoretically, you could have returned some solutions in this first-second area where a person won't really notice the computation, but they're not the optimal one yet, and that irritates me at the very least. So the tuning can matter a lot, but for heaven's sake, don't do it early. Like premature optimization is still an issue here, even if you know you're gonna need it. Because if you don't have the model for planning in your domain rock solid, if you and the SMEs don't agree that the plans that are coming out are good plans, it is not yet time to worry about performance. You need to make sure that you're producing sensible plans before you start to wrench it down and get to those faster. So after the optimizations, after the performance optimizations and the changes in model, we were seeing marked improvements in the optimizer's output versus the old approach. So here, worst first is labeled as orange, and the optimizer that we ultimately produce is the gray line. And we're still bleeding a little bit, but we actually managed to almost tread water with these plans in most municipalities according to the model. And that's a huge improvement over losing large amounts of progress in Payzer score year over year over year over year. The thing is that the way we get here is radically different than the way those folks have been working heretofore. So we get here by doing largely preventative maintenance, which means that you have some highways that really degrade quite a ways before they're repaired. And sometimes that street is Main Street, and sometimes that's unacceptable. But in general, we're advocating for a very different type of care for highways by producing these plans. So ultimately, there's a hearts and mind argument here to be made, right? There's a hearts and mind argument to be made here. So luckily, the plans weren't going immediately to municipalities. There was a dream of having this thing be SaaS and have any agency have an account, sign in, and generate their thing. In practice, where they were as a startup, they were doing this as a professional services gig. So they had their own civil engineer fronting the plans that were generated by the AI and talking through them with the agencies that were buying their planning services. And that proved to be critical because the civil engineer could convince those people that a different approach to highway maintenance was practical in a way that a screenshot, a report, an essay was not going to be feasible. So it ended up being absolutely necessary that the human was walking the potential buyers and executors through these plans because it was such a new way of thinking. The other big issue that came up with these plans was that they weren't done in the way that the planners thought about it themselves. So the solution strategy that we took was actually kind of alien to the engineers that built these plans previously. Because there are two big ways that those plans are changed once they have one in hand. When they're arguing back and forth with the mayor or whoever the power that be is, these two types of changes come through. Don't do that improvement on that highway. Instead, take that money back and use it somewhere else. And alternatively, this is my pet project this year, right? The Centennial is happening. We are repaving the parade route because we will not be embarrassed by it. And I don't care if it's not exactly the right way to use the money from the highway's perspective. It's right for the town. So those changes came in, and it was hard for our system to adapt to those. Not impossible, but it was off of the strategy for solving. So it was off of the strategy for solving, right? And so having no goods and having must-haves, you can get those in tree search. What you do with the no goods is you just delete that action from the space. And what you do with the must-haves is you take your pristine planning state and then take a fixed sequence of actions and then plan from that node in the tree. It's pretty straightforward. But what would have been nice is to have built it in from the outset. So tree search enumerates down the sequence of possible actions, but local search is a different search technique that what it does is it takes a potential plan and it says, you know what, that action right there, I'm going to change that one. And we're going to see what the resulting quality of that plan is. And changing elements of a plan is so much closer to the way those engineers work that if I had known that going in, this was ultimately the right decision, because then when they interact with the software and see the second and third and fourth plan that it produces, they won't say, well, why the hell did everything change out from under me? We had to do a lot of work to make sure that portions of the plan stayed fixed every iteration that we wouldn't have had to do if we took this other solving strategy. So that is, from 50,000 feet, how we applied AI to the problem of highway maintenance. We spoke to the engineers about what the problem was. We worked with them until we were producing plans that were sane. And then we wrenched on the system until it produced those plans very quickly. Remember, though, that when you think about AI, a lot of people are thinking about chat interactions, building reports, or doing predictive maintenance style things with ML and SageMaker, right? But it comes up everywhere. And if you're looking for opportunities and you say, well, it's only in physical devices where things may fail, or it's only in user interactions, you're going to miss some really cool opportunities to do applications. Just because it says AI doesn't mean it's not software, and so you should use all of the best practices that you've been practicing all of this time when you build it too. And even if you can build some cool whiz-bang solution, it really helps if it meets the users where they are, because ultimately those are the folks in most cases that are going to be doing something with the output of the program and making whatever it is you're helping them do a reality. I appreciate all of your attention. If you've got questions that you've held to the end, I'm happy to take them now. Yeah.
I was wondering if you ended up trying to use AI to help with the mapping part?
So the question was whether or not we used AI to help with the mapping part. There are, when we were slicing this project off, what they wanted to do was soup to nuts. We want to image the highways, do the scoring, do the planning, and actually do something called build, operate, transfer, where they took over ownership of the roads and leased them back to the city over a period of time before returning them. It was on the roadmap, but it wasn't the critical differentiator for the client. So it was the next thing to do, and we never got around to it. What they ended up doing was acquiring a company who does. But yeah, there are a bunch of startups in that space. I think actually one or two around here. Yeah, anyone else? All right, well, thank you so much for your attention. I'll be here if you have more.